recording it. Today is lecture 7. Lecture 7, so 01/29/2020. So it's chapter 4, Lyapunov stability theory, right? So that's what we are doing. We are trying to kind of make a connection between stability of nonlinear systems, right? We are dealing with x dot of f of x type of systems. When can we say this system is stable, asymptotically stable, globally asymptotically stable, or unstable, right? So those are the things we are trying to make. And last time I kind of gave you that there's an energy kind of concept happening here. If energy is always positive except at origin, and if we are able to show that V dot is negative everywhere except the origin, that means system is asymptotically stable, right? If it is V dot is negative semi-definite, we can say that at least it is stable. We cannot say more about asymptotically stable. So today we will do that proof. This maybe we might have one or two more proofs, but this proof might be little involved or things like that. Maybe after the class we'll go and get a donut or a whatever. I keep forgetting this. But what do you have after the class?
I'm actually meeting your favorite, Zach and Heath, for lunch.
Zach is who's Zach?
Zach, you don't know who Zach is? Zach?
Oh, our Zach.
Zach Wells, yes, your favorite friend, your best friend.
Yeah, okay, but okay.
Zach and Heath.
We will go.
Okay.
You can go with us and then you can join after
Okay.
5 minutes.
Okay.
And we will grab a drink or something.
Okay.
A beer. Oh, I should not say on public record here. It's recording.
I forgot you are recording.
So, anyways, right? So we want to prove this. So this was the theorem again. Let me just from previous class. So it was saying that let x equals to 0 be an equilibrium point for x dot equals to f of x, and let origin be part of that D, right? D is basically subspace of Rn, so this is D, and your origin is basically kind of inside D. Let V, the Lyapunov candidate function, operates on D, be such that 1. So we are saying what are the properties of V. V is continuously differentiable. Second, V is PD, positive definite on D, right? And then basically we are saying these two things. X equals to 0 is stable if V dot is negative semi-definite, right? That means V dot is less than equal to 0. Equal to sign is important here, right? Because of the equal to sign, we cannot say that it is asymptotically stable, but just stable. And we'll prove it. B, x equals to 0 is asymptotically stable if V dot is negative definite, right? So that's the thing. Let's prove it. And okay, so proof. Bear with me and the proof. Okay, proof. We'll keep going back to the theorem, but okay. So let's fix an epsilon. You remember the stability's definition? That if you choose your initial condition within a delta, right, x of 0 is less than delta, and the proof was again, but the definition was that if you choose within delta initial condition, and if you can say that for that delta there exists an epsilon, and your trajectory is bounded by that epsilon, right? then system is stable. So that's why we are fixing an epsilon first. Like, okay, let's say we have an epsilon. Fix epsilon greater than 0. We can always, whatever assumptions we are making, we can make them red. Okay. And given given D, we need to ensure that so let me draw a picture here also, like one portion of that screen. I think we can kind of give it to the picture here. Okay, so this side I can write the math part, but here is our picture. Let's say our D is this. So our awesome subset is this. So this is our D. That's the D which we are talking about. And in this D, what I'm doing is so this epsilon, that if you remember, the delta and epsilon were kind of balls. So if you, I don't know if you remember the stability definition, which was saying if x of 0 is less than equal to delta, and then if x of t is less than equal to epsilon, was that. So what does this mean, this norm? If we, that's kind of a ball if you take it a 2D, right?
Shouldn't that D be a convex subset of real number?
No, D is just a subset. Right now we are just so you're saying it should be
if I choose 2 points from there and if something in between lies outside.
Yeah, the concave convex thing, D is just a subset of values. Right now there is no concave convex, not even closed. It's just said that because we will within this D, then we'll make those arguments. Okay, for now. And if it is there, I will come back to you. I don't think there is any convex concave properties on D yet. Okay, so so having said that, BC. Can I get the book? Just one second. Just want to ensure the terminology here in the notes as well. Maybe I can use book to do that. Okay. So epsilon, let's say we fix this epsilon for now, and then let's say we choose an R, right? Choose R such which is between 0 and epsilon. Okay, that means it never touches 0, so it is always greater than 0, and epsilon is included. So this kind of square bracket means epsilon is included in the boundary, and the open bracket means that 0 is not in the boundary. So it can go it can go close to 0, but 0 will never be. But so it is, the R will always be, so R is a number between 0 and epsilon. It can be equal to epsilon, but it cannot be equal to 0. So that's the number I'm choosing. Okay, and I'm defining a ball B of R, right? BOR equals to is defined as X belonging to R and such that your X will make our figure a little bit. Such that X is less than equal to R. Less than equal to R. which is a subset of D. So I'm saying that this is the origin, right? This is the origin, and I'm choosing a ball which is defined by this, means where X is always less than R, right? So that means I can draw a ball right here. Let's choose a color blue so let's say this is the radius R, right? Something less. So we are drawing a ball. So all the points in this ball basically means the distance from the origin is less than R, right? That's what exactly means. So this our blue is, we call it B of R, like this. And B of R, because I have chosen such that B of R is a subset of D, right? Right, so that's one, and we'll come back to all the things later on. So now next step is let. Right now I'm just making a picture, and from that picture we will be giving the proof. So just so next thing is let alpha equals to minimum of X equal to R. So if I go and drive on this trajectory, right, where X equals to R, it's a circular trajectory, right, and find what points. So I'm computing V of X at every point on the circle. So V of X, something like, for example, V of X equal to half X squared, for example. So I am going around this ball. If it is, of course, if it is something simple like this, of course V of X will be same everywhere because it's kind of distance. But I'm defining an alpha which says minimum of Vx on the boundary of this circle is defined as alpha. So minimum energy, its alpha will be a positive number because it's not an origin. What is the property of V of X? V of X is positive, always positive, except at this origin, right? If V of X at this point is equal to 0, everywhere else it is positive, right, in D. That means if I drive around this boundary and keep recording my V of X, I'm saying what is my alpha? Alpha is the minimum of that number. So wherever, okay. So once I do that, so then alpha is greater than 0, right? No doubt about that, right? That's undoubted, right? So V of X is then take, and if you see, because then take a beta, we are just defining a beta which is between 0 and alpha. That means beta neither touches 0 and neither it touches alpha. It means they are like the boundaries are not included. Let's choose a point beta and define a set omega beta where, so there are two types of sets. One are energy sets and one is a distance set. Distance set is something like balls. This B of R is a distance set where I'm defining the mod of X is always less than R. And there is an energy set where I'm saying the energy is always less than equal to this value. So there are two types of sets that we are kind of drawing here. One is the ball kind of architecture where we are talking about saying a distance kind of thing, that my distance is less than R. So that looks like a ball. And energy sets are defined by omega beta where we are saying in this set your energy is always less than this number, right? Because so that's the whole idea here. Okay, so we're defining a set omega beta where all the points X belonging to beta BR. So we are choosing all the points in this ball here, right? Right, and we are computing energy for all the points. So what will be all the points? Any point in this ball, basically, and we compute the energy, right? And X belonging to BR, we find a set where V of X is less than equal to beta. So this is a new set we are defining where X for all the x's in BR, what are the points where V of x is less than beta? Right? This is the set width. And by the nature of the definition, you know that this set will be inside this BR, right? Because at the boundaries, we know that V of x is alpha, right? Or alpha, or always minimum. So V of x, alpha is what? Alpha is the minimum, is at the boundaries of this. So V of x. So how was alpha defined? The minimum energy on this point. So any point inside this will have energy less than that alpha, right? So that means this set alpha omega beta will be contained in B of R. But the picture, that's a circular looking thing because that's a distance. Here things will be an ellipse because your energy can be, so I can draw this as a red thing, and we say let's draw this omega beta, something like this. It can touch these boundaries, like let's say these are the points where it was equal to alpha. So this is omega beta. Okay, so in this set, if I just color it, your energy is always less than beta. Okay, so let's see if I can erase this again one more time. Draw it.
And beta is any number from 0 to alpha?
Yeah, beta is any number.
Arbitrarily?
Just an arbitrarily chosen number. Okay, so it can be. So it's kind of elliptical energy omega beta, right? So BR omega beta. Got it? So now let's discuss the property of omega beta, right? So omega beta, of course, is inside, is a subset of BR, right? So that's not a problem. But what are the properties? If you look at our definition, we are saying in D, V is positive, right? PD. And we are saying, let's say, V dot is, let's say, negative semi-definite. What does that mean? So if I am in this set omega beta and my V dot is negative semi-definite, what does that mean? That means the energy will never go above that point, right? You will always stay within that omega beta. If you are in omega beta, you will stay in omega beta. At least it's conservative. You can, that property was valid for a whole D, but now we are talking about energy curves. We're saying that at the boundary energy is alpha, but inside boundary energy is less than alpha. But even more, because V dot is so inside omega beta, our V dot is what? It is less than equal to 0. We are assuming the negative semi-definite for now, right? We are saying. So then that implies what? That implies V of x will always be less than equal to V of x 0, right? So let's say I start at some initial energy and it is negative semi-definite. That means even if it is not increasing, or even if it is not decreasing, at least it will not increase. If it is less than equal to 0, then it is decreasing. Even if it is equal to 0, it stays the same, right? So you will not, your trajectory stays within omega beta, right?
So can you explain why the shape is ellipse?
Huh?
Why the
Energy curves kind of like
That's a constant energy.
yeah. So if you see there are v of x equation, right? Let's say I draw half x square plus half x1 square plus half x2 square, right? So this is basically, if you see a matrix, it will be like, let's say half, I think it is half into 1 0 0 1 type of matrix multiplied by x transpose x. But so this way it will be a circle. If you draw if you draw equal to c, something like this will be a circle. But there can be places where this is 1/4, and there can be a like equations where this is 0.5, this is 0.5. Those are equations of ellipses. So ellipse is a more general curve than a circle. Circle is a special case of ellipse when major and minor axes are same, but it can happen that they are not same. So by nature itself it is a elliptical. V of x is an elliptical trajectory. Okay, all right. Good question. Yeah, I never thought it before like that, but even that you asked it makes more sense. Okay, so yeah, because our V of x is a general equation, circle, ellipse, higher order ellipsoids. I know I'm just drawing a 2D picture, right? It can be an ellipsoid or things like that. So having said that, for all t greater than 0, we can say that if you are in beta here, right, somewhere here, that means v of x 0 is something, and then b dot is negative semi-definite. That means at least if it is negative semi-definite, you will be on this kind of curve, energy curve, energy level, right? This whole ellipse can be considered as energy curve. You will at least stay there, or you go below, but you will not come out of it. So that's the kind of logic we have here. Okay, clear? So now let's go back to our proof. Okay. And these energy sets are omega beta is a compact set. There is a definition I can give you of compact set. I think there was somewhere in the notes it is given, compact set. Okay, omega is a compact set. There is a theorem 3.3. Now we are applying, because it is continuous, the v of our f of x is continuous, right? We assume that, and it is locally Lipschitz. That is always an assumption on f of x, right? X dot equals to f of x, right? There is a theorem which says that if it is locally Lipschitz, so we are saying it is locally Lipschitz because it is continuously differentiable, right? That means it is locally Lipschitz. And now we are also saying that it will never exit that compact set omega beta. What does that mean? That it will have a solution for all t greater than t0, right? If you remember your theorem 3.3, right? From 3.3, you can say that there is an unique solution for all t greater than equal to t0. Why? Because it is locally Lipschitz and it is not leaving this set. That was the theorem there, right? So we have shown that if it is negative semi-definite, it will not leave that omega beta set, which is compact. So therefore, first part of the proof, at least, is we are showing that there is a solution, unique solution, and that's important. Okay, so we have proved that there is a unique solution there because it does not leave that set. Okay. So now next part of it proof is this. Let's go. So as v of x is continuous, right? Of course, that's the one property of our v of x is continuous and continuously differentiable. Vx continuous and v0 equals to 0, right? At 0, your v of 0 is 0, right? That's a property of our positive definite. Like it was positive except at the origin. At origin, v of 0 is 0, right? 0. There is a delta greater than 0 such that, so if x of less than equal to delta, then v of x is, which implies v of x is less than beta. Right? So what I'm saying here is if I can choose my initial conditions within this, so I'm defining another delta. So this is b of delta. Right now I don't know if it is bigger or smaller, but I'm saying that I'm choosing delta such that within that boundary, this is the case. So this is the equation of a circle kind of thing, right? And we are saying that if it is less than this energy beta always, that means this thing will lie inside omega beta, right? That's the logic here. So how do I know that this circle, that x of delta, that b delta, this I call as b delta. How do I know that this b delta has to be inside this omega beta?
This is
If I can ensure that
this theorem 3.3 that we used is only defined within this
omega beta,
Yeah.
for omega beta, yes.
So that means for this to hold, it must be inside.
No, but I'm not applying that. I'm just that is a different issue. We are saying that it will never leave if you start within the. Now I'm saying where should I start within omega beta? So if I choose a delta in which v of x is always less than beta, that circle will now be within, it will be inside omega beta, right? So this is omega, this is b delta, and in b delta I'm saying v of x is less than epsilon, or less than beta. V of x is less than beta. That means v of delta will be inside omega beta, right? The energy ellipse, this one, inside the red circle. See, on the red circle, energy is maximum at. So, if you are saying v of x is always less than beta, that means this will have to be inside, because outside energy will be more than omega beta, right? So now we can say, if we are talking about these three things, that means if you have to say, that means b delta is a subset of omega beta and omega beta is a subset of br. True, right? In this picture here, so this is br, blue one, this is the topmost. So if this is inside omega beta and omega beta is inside br, that's what I'm writing here, right? True, right? That's true. Now let's, so if x of 0, so now this is see, these things are, because I have to give that whole definition type of proof that if I start within delta, I will not leave omega beta. So epsilon will be that the outermost circle kind of thing, right? So that's the logic here. So if x of 0 is a b delta, that means if I am in the innermost circle, right, we have, I think I can redraw that picture. This is br, this is omega beta, and this is B delta. So that means if x of 0 is somewhere here in B delta, right? And we know that within B omega beta, this is negative semi-definite. So this trajectory will do whatever it does do, but it will never leave this, the red one, right? The red one. So what does that imply? If I start in that implies that x of 0 belongs to omega beta, which implies that x of t belongs to omega beta, right? Even though any trajectory omega beta, because it will never leave, and which makes x of t will also be belonging to BR, because BR is the outermost boundary, right? So if I start in delta, I will never leave B of R. And B of R, how was B of R chosen initially? R was between 0 and epsilon. So that is my, so if I'm saying I start within delta, that is my initial condition, I will never leave B of R. B of R is the, like, because here it might be touching, right? So I will never leave, this is a conservative estimate, but I will never leave. So this is your delta epsilon stability condition. Hence, your system is stable when it is negative semi-definite, right? So that negative semi-definite thing created a magic, right? We carefully chose our subsets, so you never leave it, and then somehow we show that it never leaves BR. So you start in delta, but you never leave BR, for sure, guaranteed. That means system is stable, right? So here we can give the statement, right? So we can say then x of 0 delta implies that x of t is less than x of t is less than r, less than equal to epsilon, for all t greater than equal to 0 for now. So that means, what is this? This is exactly the definition of stability. So that means system is stable. If V is positive, definite, and V dot is negative semi-definite, your system is stable, bounded by BR at least. Okay, so that's one proof. Now we are going to
Bounded just by BR is not even bounded by omega B?
BR is the
bigger circle, but I
yep.
thought it was even bounded in the red one.
No. BR, the inner circle is like energy level is even less than any point on BR. So the inner circle omega B is in. Yeah, exactly. You are right. It will never leave omega beta.
Right.
That
so
means
it's even more.
Yeah,
okay.
But omega beta is the condition for energy. You are saying your energy will never go more than this. But we have to give a condition that your x will never leave a boundary. So if you
that's
see,
what you mean by defining a space versus an energy.
Yeah. So
Okay,
there are
I got
energy
you.
curves versus
Okay.
x curve, saying x is not. So the inner circle and the outer circle are giving that if x is less than delta, it will never, the x value will never go more than less than greater than r.
Okay.
But the inner red circle means
And
your
the
energy will never
for
go
that
out of
X
whatever
will not
you
go
started.
out. Okay.
So
Okay.
that's why this
Okay.
was important. Good catch.
Okay.
Right? You got the point here? So that's why we could argued, yeah, you can say it will never leave omega, but I don't know what omega beta means in terms of x.
Right.
Will never less.
So the energy corresponding to that X will not exceed the omega beta, but X itself will not exceed the B,
BR.
the
Exactly.
beta R,
Yep.
BR. Okay.
Yep. So that was needed. That's how we needed to put this condition to give it a stability.
Okay.
Okay. So that's one case.
What is the what you have boxed in there? You're saying like x is basically bounded by r for all time,
Yep.
which is
For
then bounded
for
by
all
epsilon?
t greater than 0.
Okay, but that's bounded by another number. epsilon.
Yeah,
So what's
R
the
is between
epsilon?
0 and epsilon, right? You can choose any number. So R
Oh.
that we chose was between 0 and epsilon.
Okay.
So it's flexible. You can okay. So now going further for our proof, right? Means hence we can say x equals to 0 is stable, right? That's our stable equilibrium point, right? Proof. So now let's going further. Now let's say 4.4 holds as well. So what is our 4.4? Or now we say we were showing initially that v dot is now strictly negative in that d. What happens then? Now initially it was negative semi-definite, but we are saying let's say v dot is strictly or it's negative definite now, right? So now to show asymptotic stability, if that's the case, we are showing that x of t has to go to 0. Whatever delta it starts in, instead of it has to go to 0. But that's what we want to show now, right? So So the proof for this is pretty easy. Let's say that v dot x, right? I can say that v dot x, we define a number called gamma, which is minus of this, which is a limit, or is the maximum of d x so within that, if you see if you remember our b of r, right, this is b of r. In this b of r, because we know that in d itself it is negative definite, right? So we are saying within this ball, if I find the maximum rate and we say that number is alpha, this is just for the proof, right? So maximum of v dot is minus gamma, let's say. So if that's the case, then I can integrate it, right? Because if I know v dot, I can integrate and find out what will be v of t, v of x of t. That will be v of x0 integration of 0 to t of v dot x tau d tau, right? What will be this? This will be like something like v of x0 minus gamma t, right? So see, v is decreasing, we know that, and if we just improve, that means your v will always be less than v of x0 where we started and keeps decreasing, right? But like how much it will increase as soon as it reaches 0, because it is a negative definite where v dot is equal to 0 at x equals to 0. So it stops. This gamma basically stops, and then the energy basically goes to 0 when it reaches origin. So basically you start at anywhere. So what we are saying, if you are in omega beta, where negative, if you start in omega beta, specifically when like if we go back to our picture, right, there's this omega beta here, where in this is our x is delta. So if we start here, energy is always less than omega beta, compact set, and now energy is always decreasing because it is in omega beta, and eventually it goes to the origin. And when v is equals to 0 is when x equals to 0. V dot is also equal to 0 when x. So that means it goes and x goes to 0 basically then, right? as t goes to infinity. So that's the kind of proof we have. So if it is negative definite, then v of x goes to 0. So your energy definitely goes to 0. So is v dot, and energy and v dot are 0 only if x equals to 0. So what does it imply? That means x also goes to 0, right? So what is this showing? This showing that v of t is going to 0 as t goes to infinity, right? This implies that x also goes to 0 as t goes to infinity, right? So that means negative definite means that it is asymptotically stable. Got it? So let's do a couple of examples to show this. And let's do an example now first. Sure. Thanks. So example. And if your v of x is radially unbounded, then system is globally asymptotically stable. That means your omega beta can be extended to a bigger space, infinite space. So that example is this, our inverted pendulum example, right? x1 dot equals to x2 and x2 dot equals to minus a sine of x1 minus b of x2, right? So it's an inverted pendulum problem with friction, right? So let's say we choose a Lyapunov function called v equals to a 1 minus cos of x1 plus half x2 squared. So that's my Lyapunov candidate function. Is it positive definite? So this is only 0 if x1 equals to 0 and x2 equals to 0, right? This quantity is only 0 if x1 equals to 0 and x2 equals to 0. By in other words, x equals to 0, right? Otherwise it is always positive, right? At x1, at x1 equals to 0, this is 1, so this becomes 0, and then x2 equals to 0, but there is no other way you can make it 0. Otherwise it is always positive, but it is not radially unbounded because of this cos of x1. So now let's see how would you find v dot. So next step is to find v dot. So v dot will be simply v dot is del v by del x into x dot, basically, right? So del v by del x will be first with respect to x1, it will be, what will be it, a of something, a of sine x1, right? So see, it's already minus, so differentiation of cos is minus sine of x1, and minus becomes positive, so it is a sine x1. And then the other part is with respect to x2, which is just x2, right? Multiplied by x2, a minus a, so this is del v by del x. This is the Jacobian of v with respect to x, means with respect to x1, with respect to x2, multiplied by x dot, which is x1 dot, x2 dot, minus a sine of x1 minus b of x2, right? So when I multiply that, it becomes a x2 sine of x1 minus a x2 sine of x1 minus bx2 whole squared. This cancels out, this cancels out, right? So it comes out to be minus bx2 squared. V dot comes out to be what can you say about V dot? Is it negative semi-definite? Is it negative definite? What can you say?
Be negative, semi-definite.
Yes, because if there is no x1, it is 0 at x2 equals to 0, right?
Everywhere else is negative.
So you don't know what happens. So it is negative semi-definite. It is not negative definite. For negative definite, there should have been a term of x1 also. See, negative definite means V dot equals to 0, or V dot is also, V dot is negative except the origin. That is the definition of negative definite. But this quantity here is, of course, it is always negative except at x2 equals to 0. But x2 equals to 0 is not a point. It's a line. Means, it is, I am saying that if it is x1 and x2, right? So x2 equals to 0 means this whole line, this quantity is 0. Meaning, it is not just 0 at the origin, but it is 0 at the whole line. So it is negative semi-definite because of that, not right? So it is. This distinction is very important here. So what can we say about this system now? This means it is at least it is sufficient to say it is stable system, right? We cannot guarantee that it is not asymptotically stable. All we get, asymptotic stable system is a stable system, right? So means at least this Lyapunov candidate function is showing that it is stable and it is sufficient that it is stable. We will do further. I know that it is a asymptotically stable system, but we need more than this to show more thing. But at least this Lyapunov candidate function is showing me that V dot is negative semi-definite, and because of that, system is stable. Okay. Now you can ask a question. That this is the crucial point here, that the Lyapunov candidate function that we chose did not show asymptotic stability. That does not mean it is not asymptotically stable. It is just saying that it is stable, which is true. But it did not show that it is asymptotically stable, and I know that it is asymptotically stable. That means you could have
Stop.
Yeah, it could have chosen. You could have chosen a different Lyapunov candidate function to show this thing. And later on, because it is most of the time it might be hard to choose an accurate Lyapunov candidate function, we will put additional conditions and show that there is no way if x2 goes, this shows that x2 goes to 0. Right? If x2 goes to 0, what happens? What are our equations? That means x1 dot goes to 0. If x2 goes to 0, right? If x2 goes to 0, x2 dot goes to 0. See, if something is constant, that means the dot goes to 0, right? So that means the second equation is this is equal to 0. Oh no, so this one. What is that equation? If that means this is equal to 0. This is definitely equal to 0, right? And now if this is 0 and this is 0, x a minus a sin x1 also has to be 0. There is no other way there is an equilibrium point otherwise. It has to. So we can impose something like this to show that if x2 goes to 0, x1 also has to go to 0. So this sufficient of having negative semi-definiteness is sufficient to show that system is asymptotically stable. This will be called, I think it will be called Barblat. What was that? What was that? Yeah, we'll get a theorem which will define this whole jazz. Lassalle's invariance principle. So this principle will be Lassalle's invariance principle. We'll get to that point when we. But right now we did not choose a proper Lyapunov candidate function. Let's go ahead and choose a proper candidate. So this is kind of. So we will go to Lassalle's there, but let's choose a general. So a rule of thumb is start with the simplest candidate function, which is always, most of the time it is V of x equals to half x1 squared plus half x2 squared, right? What is the time?
2:15.
We have 5 minutes, right? So start with this. If this does not work, then choose more general Lyapunov function, right? More general Lyapunov function will be something like, if I choose V of x equals to half x transpose px plus a1 minus cos of x1, let's say, and I'm putting some flexibility here. P is a positive definite matrix, a 2 by 2 positive definite matrix, whose coefficients I have left to be, means they satisfy the conditions of positive definiteness, but I am not right now specifically starting with the exact numbers in mind. I can later on go ahead and choose those numbers such that it satisfies both conditions, positive definiteness as well as the negative definiteness, and then we can so having said that, so P will be basically like something like P11, P12. It's a semi-definite, so it's a symmetric matrix, P12, P22. So basically there are three unknowns in this, but we know that it is positive definite. That means this is positive and the determinant is positive. If that conditions are met, this is a positive definite matrix. Okay. So if we do that, then V of x becomes what? It becomes half P11 x1 squared half P22 x2 squared plus P12 x1 x2 plus a1 minus cos of x1. Okay, so we are saying that P11, P22, P12 defines, we will choose them such that it is at least positive definite. Okay, so that our number. So right now, but I have left them, it's an open question, what are these values? P11, P12. And then start with your V dot now. Okay, you can verify that this is positive definite if these numbers are chosen in a certain way such that P11 is greater than 0 and the determinant, which is P11 P22 minus P12 squared, is also greater than 0. If these two conditions are satisfied, this is positive definite matrix, and we know that x transpose px, if p is positive definite, that is that number is always positive except at x equals to 0. Okay, so our v dot x can be written as, I'll just write it quickly. So again, same partial of with respect to x1 x2 multiplied by x dot gives me this equation. I'll just directly write it, a1 minus p22. I'm writing a simplified version, x2 sine of x1 minus a p12 x1 sine of x1. Having this flexibility will help me cancel out bad terms. Basically, I can choose p1, p2, which are so that things go away, bad terms go away, plus p11 minus p12b into x1 x2 plus p12 minus p22b x2 squared. Okay, this is what the expression we got. Now if I have flexibility to choose p22, p11 and p12, right? So first of all, I want this to go away. Any cross correlation terms are not good. x1, x2 is not good to show that it is negative definite, right? And so to do that, what we can do is now we can choose. So let's choose p22 equals to 1. Okay, so let's choose p22 equals to 1. That means that term will go away, because see, x2 multiplied by sine x1 is not helping me. That is an ugly term, right? That is indefinite term. It's not either positive or negative, you cannot say anything. So let's get rid of that. So p22 equals to 1, right? What happens? This goes away, right? Having said that, and then you can choose this, you can get rid of this. So we can say p11 equals to p12b, right? That will go away. This goes away. Now we have to remain with good terms, right? x1 sine x1 is always positive, so that's good. That means as long as p12 is greater than 0, then we are good. This term is always, see, what is the objective? We want to show that V dot is always negative, except at the origin. That is our goal, right? So what we choose, we P221 equals to 1, get rid of this equation. P11 equals to P12, we get rid of this equation.
Okay.
Right? So now, what you can do is, so see, this tells me that P12 has to be, so what are our conditions? P11 has to be greater than 0 and P11, P22 minus P12 whole square should be greater than 0 for positive definiteness. So these conditions should be satisfied for the matrix to be positive definite. Now these conditions are there, so only choice is now we have to choose either P12 or P11, right? So if I choose P12 to be, so P22 is already 1, right? So, so it is P11 minus P12 whole square should be greater than 0, right? So now I can say, let's say P11, so if I choose P12 to be, let's say P12 to be B by 2. So P12 has to be a positive number. What if I choose P12 to be equals to B by 2? Just any number. Any positive number will work here from this perspective, right? Because x sign of x1 is always positive. I want this to be positive because A is always positive. So if I put this, so if what will be P11 then? So P11 then will be B square by 2, right? So you can verify here. So P11 is B square by 2 minus P12 by square, so that will be B square by 4. So B square by 4 is always smaller than this number, so this is valid. Right? So what does that mean? That means the final equation becomes V dot x becomes, if I choose these values, becomes minus half of A B x1 minus of half B x2 squared. Oh, sorry, x B x1 sine of x1, I forgot to write. So this is always positive quantity, this is always positive quantity, that means this is always negative except at the origin. This time it will be only 0 if both x1 equals to 0 and x2 equals to 0. So this is negative definite. That means system is asymptotically stable. In the first place, we did not choose a proper Lyapunov. So you can give yourself a flexibility that let's start with just random numbers initially and then choose at the end which satisfies both the positive definite condition as well as negative definite condition. When you are choosing those P11, P12, P22 such that V is always positive definite and V dot is negative definite. So this is one way of approaching problems where a simple half x1 squared, half x2 squared Lyapunov candidate function is not working. Again, I'm not saying your life will be easier because things get tricky, but that's one approach of approaching things. Okay, so we will stop here, but we'll do more examples. There are other approaches of using general similar approaches, but this is fun. See, now what I'm saying is when we will be doing controllers, we can get away with simpler V's, because then I have a controller to cancel bad terms and keep things negative definite. That will, your life will be much easier when you will be doing controls. Proving a general stability, asymptotic stability for a given function is harder, but if you have control in hand, I start with V equals to half x1 square, half x2 square. And any unwanted term I can cancel using my U. So U equals to such that it cancels out all the bad terms and keeps the nice terms, which shows the negative definiteness. We are good, right? So that will be the kind of goal, feedback linearization kind of aspect, where we cancel bad terms which are not helping me in showing V dot negative definiteness, and we keep the terms which shows negative definiteness, or add terms which helps me in negative definiteness. So that will be like a basic control design approach you have there. Okay?
So how exactly is choosing V so that you get negative definite relate to choosing your controller?
So, see, for example, in the same question here only, right? In the first part when I was doing, for example, what was that? x1 dot equals to x2, right? And x2 dot was minus a sine of x1 minus b x2, right? Something plus u, right? U is the controller now, let's say. And we choose the same Lyapunov candidate function. What was that? That was in the book. What was that? A first Lyapunov function that we chose. What was that? A 1 minus cos of x1. Is that correct?
Yep.
Plus half x2 squared, right?
Mm-hmm.
Let's say I choose this, right? So now I have when you do this vx dot. So now I plug things in, so my equation becomes a sine of x1 into x2 plus a x2 sine of x1 minus b x2 squared plus u x2, right? Now u x2 came. And now you can choose your u such that if you have to cancel out terms to make this negative definite, things will be like this. So now you can use the control, and if it is right, you can choose u such that you cancel out bad terms. Right now there is no bad term as such, but now you can add. Right now this is not exactly the same problem I was thinking, but you can choose now. It's your controller. You can choose such a u such that the v dot is negative. What were we doing in u equals to minus kx in linear systems? We were choosing u equals to minus kx such that a minus bk has negative eigenvalues, right? The gain k was chosen such that a minus bk has negative eigenvalues. What are we doing here? We are choosing u more general such that v dot is negative definite. So that will be whole like controller design approach that we will do sliding mode or anything like that. Okay.
So your V would then be a function of U as well. So
V is not a function of u.
V is not.
See, why did u came? We have v, right? What is v? Is some x function, right? Some function of g of x or something. But when you v dot, v is del v by del x into x dot. X dot brings in u.
Okay.
So v is not a function of u.
V dot is.
V dot is a function of u, right? And v dot, because there is a u, now you can choose things such that you make v dot negative definite. Right? Yeah, v is not a function of u. U appears because of the dynamics x dot. Because v is changing because of the u, right? Because whatever changes you make in x goes and affects v. Right? So that will be the logic of choosing controllers, and it will be fun. Like we'll see how rich. You can know everything in this. This is the controller. Like you will be canceling bad terms and all that stuff, but it will still work and things like that. Okay. Great. So this shows that our equilibrium point x of 0 is stable, right? This the previous one.